Hello everyone. Today we'll be talking about a rather interesting problem, modeling heat diffusion by a cellular automata. First of all, we need to understand what the problem statement primarily comprises of. Cellular automata could be thought of as a discrete computational technique wherein a set of local rules which apply to the microscopic particle system helps determine the overall behavior of the macroscopic system at large and also helps us determine the emergent behavior of the system for a prolonged duration of time. In this particular case, we'll be using it to model heat diffusion through a thin metal bar that has application of various temperatures at designated locations for a certain specified unit of time. We'll now be moving on to a few of the essential implementation details which are required in order to properly comprehend the end results of the simulation. We have assumed a square grid which is primarily of size of 10 cross 10 for the purpose of visualization via GIFs. Apart from that, for our trend analysis of various parameters, we have varied the grid size from 6 cross 6 to 30 cross 30 in steps of 2. At each of these cells in the overall grid represent the microscopic particles of the system. Furthermore, we have assumed a padding of ghost cells in addition to our actual grid to model certain boundary conditions. We have also included them in our simulations in order to understand how their behavior affects the system in large. We have varied the concept of neighborhood, that is what happens if we actually modify the neighborhood or the trends in a neighborhood. We have also modified the boundary conditions. We'll be discussing upon the effect of diffusion rate as well as the effect of problem size in relation to this particular problem. Let's look at a few of these parameters in detail before we actually move on. Neighborhood is especially important for the case of cellular automata. This is because the future value of a current automata or a current cell not only depends upon the current value of that cell, but also depends upon the current value of all of its neighbors. There are two broad theories, that is the Moore neighborhood as well as the von Neumann neighborhood. A von Neumann neighborhood tends to look at things in a bit more traditional sense, as in we only have the four standard directions, north, east, west and south, and their contributions, whereas a Moore neighborhood takes into account the diagonal elements as well, and this helps us paint a more comprehensive picture. For this particular case, we have assumed the Moore neighborhood. Now there are multiple ways in setting up a Moore neighborhood as well. One could have a uniform or an unweighted Moore neighborhood, whereas when all of the neighbors have a uniform contribution, whereas a weighted Moore neighborhood has specific contributions from each of its neighbors. Moving on to our boundary conditions. An absorbing boundary could be thought of as having an envelope of constant temperature ghost cells, which is in this case constant room temperature 25 degrees Celsius. This is very similar to a bar being placed in a well ventilated room at a specified room temperature. The second case of the reflective boundary condition actually presents us with a situation in which the value of the boundary which we are looking at actually depends upon its immediate neighbors. This actually presents us with an advantage of holistically looking at the local hotspots in a more holistic manner. The final condition is the periodic boundary condition. In this particular case, the value of the current boundary which we're looking at actually depends upon the parameter values of the original grid, which is exactly opposite to it. Now this also tends to have a particular advantage, the advantage being in a closed system, all of these boundaries tend to have an effect on each other, and this actually helps us in accurately modeling this particular thing. The rate of diffusion primarily is a parameter which helps us understand at what rate a particular cell can transfer its temperature to its adjacent neighbors. For the first part, we shall consider two particular cases. In the first case, we'll be applying constant heat to a certain portion of the metal bar, and in the second case, we'll be applying time-bound heat to the metal bar. So first of all, let's understand the organization of the problem. We'll be considering a 10 cross 10 metal grid, wherein we'll be having two local hotspots, as in the northern part of the primary diagonal will have an application of a temporary area of 100 degrees Celsius, whereas the lower part of the primary diagonal shall have an application of 0 degrees Celsius. As we can see in the first case, when we have applied the heat and as well as the cold temperature for the entire duration, the absorbing boundary, reflective boundary, as well as the periodic boundary tends to reflect its own behavior, as in the case of the absorbing boundary, since the boundaries itself have a constant room temperature, therefore the overall equilibrium temperature also tends to be more or less around the room temperature as well. Of course, this is excluding the specific hotspots of the hot and cold temperature. Furthermore, for the reflective boundary, one can observe the effect of the local temperatures upon the entire system, as in the area around the region where we have applied a hotter temperature of 100 degrees Celsius tends to be warmer, whereas the other case tends to be extremely cold, and we have a slight gradient as we move from one region to another. Finally, for the periodic boundary case, we observe a symmetric figure because the periodic boundary condition tends to have a holistic outlook towards the entire system, as we have the effect of opposite dimensions upon each other. We can now see the time required till equilibrium as we vary the problem size. Now for the visualizations, we had considered a 10 cross 10 metal bar, but now we'll be varying the size of the metal bar from a 6 cross 6 dimension to a higher dimension based on the specific boundary condition. One can observe that the absorbing boundary tends to take the least time, followed by the periodic boundary conditions, followed by the reflective boundary condition. In the case of the absorbing boundary, since we already have a fixed boundary temperature, therefore the overall equilibrium condition tends to be achieved quickly because there is not much variation. For the case of the periodic boundary, since we'll be having the effect of opposite boundaries upon each other, therefore the entire system gets shuffled in one way or the other, and we also tend to receive the equilibrium a bit faster. However, for the case of a reflective boundary, we need to make the whole system come to term to an equilibrium while accommodating the local conditions as well. Now, the local effects tend to take some time to aggregate up to an equilibrium condition. Therefore, the periodic boundary condition takes the highest number of iterations if we consider the same problem size for varying boundary conditions. We can also see the variation of the time required till iteration as we vary the diffusion rate from 0.05 to 0.12 or 0.125. This is because as we decrease the diffusion rate, the amount of heat which will be transferred from one cell to another would be slower. Therefore, the time required to achieve the equilibrium would be correspondingly higher. Similarly, if we increase the value of R, the heat transfer is faster and thus the equilibrium condition is achieved faster. This holds true for all of the boundary conditions. We shall now consider the case where we'll be having the same conditions. The only difference being we'll now be applying the hot and the cold region for a specified duration, that being 10 iterations. One can observe that for the absorbing boundary, even though the overall tendency tends to remain the same, but we receive equilibrium much faster than the one in the previous case. Now, why does this happen? This happens because since the overall effect of anomalies, that is the extremities of the temperatures, that tends to disappear quickly and the overall precedence is more towards the room temperature. Therefore, we achieve equilibrium quickly, and on top of it being an absorbing boundary, the equilibrium is achieved even faster. Another interesting thing to be noticed is that after a certain problem size, the number of iterations till equilibrium tends to be saturated. Now this actually happens because after a certain point, since the area upon which we have applied the temperature anomalies is fixed, thus the overall effect it tends to have on the entire matrix or the entire grid is not that significant, and the iterations more or less remain the same. This effect is not observed in most of the other cases, and that's because most of the other cases take a huge amount of iterations to reach the saturation point, and that is often not computationally feasible. As we move on to the reflective boundary cases, we again see a similar trend. The iterations till equilibrium is again lesser as compared to the previous case. A similar trend can also be observed for the periodic boundary. One can clearly observe the effect of a temporary anomaly to that of a permanent anomaly in this particular case. That is a permanent anomaly tends to have a greater effect on the overall system equilibrium as compared to a temporary anomaly. We shall now be moving on to a second major simulation. In this particular case, we'll be varying the overall temperature of the metal bar from 0 degrees Celsius to 25 degrees Celsius to 50 degrees Celsius. We'll also be keeping the hotspots or the temperature extremities to be the same as that of question 1. The overall trend of the various boundary conditions still remains the same. The absorbing boundary, on the other hand, has varied equilibrium endpoints because the final outside boundary has a constant application of temperature depending on our initial stage, Since in this case the local temperature tends to propagate throughout the entire metal bar, therefore we more or less reach a condition wherein the final equilibrium states are more or less the same. Similarly, for the periodic boundary condition, we can say that since we'll be modeling the overall system as a whole by considering the effect of the opposite boundaries upon each other, therefore still the overall boundary condition more or less reaches an equilibrium value so as to highlight a holistic view of the system. Furthermore, we can also see that for the periodic and reflective boundary conditions, when we have the initial temperature is 50 degrees Celsius, we obtain the equilibrium faster as compared to 25 degrees Celsius, which in turn is faster as compared to 0 degrees Celsius. Our local extremities are 0 degrees Celsius or 100 degrees Celsius, therefore both of them approximately try to reach an equilibrium endpoint which is close to its midpoint. Therefore, when we itself have a room temperature 50 degrees Celsius, the variability in data is less and the equilibrium is reached quickly. On the other hand, when we tend to stray away from it, the overall equilibrium tends to take a slightly higher amount of time. Our next simulation mainly focuses upon the effect of a weighted mood neighborhood. These kind of problems or these kind of strategies are generally useful for problems where we need to define certain condition based on the current situations we are in. We tend to see that even though the overall tendency of the absorbing boundary conditions, periodic and reflective, tend to remain the same, that is in terms of their behavior. However, there is a difference in the way that they achieve the equilibrium. Even though the absorbing boundary still takes the least amount of time to reach equilibrium, however, the reflective boundary condition no longer takes the highest amount of time to reach the equilibrium, but it's rather the periodic boundary condition which takes a higher amount of time. Since we're assigning the weights to each of the directions, and the periodic boundary condition is in a sense a way of representing the local values in a more prominent fashion, the values get reassigned in such a way so that the local values are taken into account in a better way and the equilibrium is reached faster. This is a classic example of where the effect of local contributions via weighted diffusions tends to help us achieve an equilibrium quicker. In this particular case, we'll be considering a metal bar of dimension 1x5 and initial temperature 100 degrees Celsius and placing it in a room of dimension 15x15 and with a room temperature of 25 degrees Celsius. We'll be observing the variation of the temperature of the midpoint of the metal bar as well as the temperature of the corner point of the metal bar. Now we can see that for each of the boundary condition that has been specified, they more or less tend to have the same behavior as was expected from them and as was seen in our previous experimentations. However, an interesting thing to notice is that in both of the cases, even though the midpoint and the corner point tend to achieve the same value of equilibrium after a larger amount of time, but the middle point takes a larger amount of time to reach the equilibrium, whereas the corner point achieves it faster. The corner point only has one neighbor which is of higher temperature and the rest of the neighbors are of the have an origin of the room temperature. That is why it achieves its room temperature faster, whereas if you take the case of a midpoint, we see it has two neighbors which are of the origin of a metal bar and has a higher initial temperature. Therefore, we have a bigger effect of the metal bar's initial temperature on the midpoint rather than on the corner point. That is why it takes a slightly higher amount of time to reach the equilibrium as compared to the corner point.